told me the cracks weren't showing up until they showed up in Japan. So they'd ship them out of Brooklyn, and by the time they got to Japan, they had cracks. So they brought these. Actually, some of the cracks have extended over time, or they did for the first few months after they brought it to me. But there's cracks in here. You can look on the inside, and you can see them. See light through there. Okay. But I noticed that the cracks were on the top, which was another clue. So it was delayed cracking. I mean, hydrogen cracking is called delayed cracking. I noticed they were at the top, and I know that when you take a flat plate of this type of steel and form it, you get the maximum deformation as you roll it up like this up here. And I went and got my little magnet. This is the one I was using at the time. It's a neodymium iron boron magnet. Okay, very magnetic up here, hardly magnetic down here at all. In fact, actually it's an aluminum bottom. I talk about the aluminum bottom in adhesive bonding lectures, but anyway. So, and you can go up the side and you can feel the increase in magnetism as you go up, because that steel, as it deforms, it turns magnetic. It's called a transformation-induced plasticity steel, a trip steel. Not stainless steels, but they've developed lower alloy steels that can give them like 150 KSI for sheet steel for automobiles now. Actually, we've known about trip steels for 80 years, but they now are using them, starting to use them for very high strength steel in automobiles now, where when you deform it, it transforms to martensite and becomes very hard. Usually with martensite, you have to quench it. Okay, any other questions? Okay. So this is, I talked about distortion, and there were a couple of things I wanted to show you. This is actually for 5083 aluminum, electron beam welded from a 1/4 inch, 6.4 millimeter, to 38 millimeters, which is about 1.5 inches thick. And if you look, this is nice and straight and flat. So are these. As you get up to about, this is probably 3/8, and I told you 3/8 is where you could get the maximum distortion. You don't get distortion here because it's not a V-shaped weld. Once we start getting into the more V-shaped welds, and these are actually probably multi-pass welds up here, you get more and more distortion, okay? Now, if the whole thing is restrained, you don't get distortion, you just get huge residual stresses, and you'd have tensile residual stresses right there. You'd have compressive residual stresses on the bottom, okay? And that was what, so far as that goes, the General Electric was finding with their stainless, they had stainless steel welds in these safe reactor safe ends. So these are like 2 or 2.5 foot diameter pipes where you'd flood the reactor with borated water if you had a problem. You'd quench the reactor by flooding it with borated water. And the problem is, those pipes were 1.5 or 2 inches thick, and they had tremendous tensile residual stresses, and they were on the inside. One of the things they did is they developed welding procedures in the future that created compressive residual stresses on the inside where it was in contact with the water. If you remember, we've got 3 things: material, stress, and environment, that can lead to stress corrosion cracking. I told you that stress corrosion cracking, many times people, well, I'll say 70% of the time, metallurgists kind of lump hydrogen embrittlement and stress corrosion cracking together, but they are different. I will now tell you the secret of the difference. And the secret is, one occurs at the anode and the other one occurs at the cathode. Stress corrosion cracking occurs at the anode, hydrogen embrittlement occurs at the cathode. Why? Because the corrosive species in corrosion are usually negative ions, and so they go to the anode, which is positive. And if you try to remember all this, just like high school chemistry, you can't keep reduction reduction at the cathode, straight. But nonetheless, hydrogen embrittlement, you got a positive hydrogen ion that wants to go to the negative electrode, which is the cathode. So hydrogen cracking occurs at the cathode, stress corrosion cracking occurs at the anode. If you're not worried about which one's positive and which one's negative, you just call them all, sometimes metallurgists just lump them all together and call it stress corrosion cracking. Because the susceptible microstructure, of which martensite is the worst, because it's the hardest, presence of stress, it doesn't really, the higher the stress, the easier it is to crack. And the environment is either a negative ion or a positive hydrogen, and that's what makes the difference, okay, so far as that goes. I bought myself a new red one, which doesn't work any better. Okay. I have a new blue one on order. I also bought a new, this is the cheapest one of all. Cost less than $10. It also is a LED light. Isn't that neat? Anyway, so we have problems with distortion. You can lower the distortion, or the amount of distortion varies with the amount of heat to the workpiece, and this is out of Sindo Ko's book on welding metallurgy, where he basically shows heat input to the workpiece versus power density of the heat source for gas welding, arc welding, and high energy electron beam welding. And the real difference here is you get a very V-shaped weld here, less V-shaped in arc welding, and high energy electron beam you can get very parallel sides, and so there's no preferential distortion, greater shrinkage at the top of the V than the bottom of the V. So if you want to look at density of the heat source versus distortion, you'll find that it varies in that manner. And here's something else out of his book, which is looking at gas tungsten arc welding, which is an arc welding process, makes a very V-shaped weld, versus electron beam welding. The distortion angle alpha goes from near zero to very high values depending on the thickness of the material. This is a plot that shows the heat intensity, power density, in watts per square centimeter as a function of productivity. When you go through the fusion welding lectures, you'll get this in some detail because I wrote it. Anyway, it's something I did 25 years ago. Okay, so that's some more on distortion. Now I want to go to, I want to go to preheat first. In the meantime, we can start handing these out. Yeah, you can hand those around. Okay, so we have preheat and postheat for welding, and we use them in lots of different materials, not just steel. So we might, but in steel, there are kind of three levels of preheat that I talk about. I'm not sure I've ever read anyone else talking about it. But if I'm preheating from 50 to 100 degrees Fahrenheit, the structural welding code says you shall not weld unless you're above 10 degrees Fahrenheit, which is sort of ridiculous because you could have frost on it, okay? But the structural welding code, we're usually welding lower strength steels, okay? And the preheat requirement is not as great. I told you it's almost impossible to take an A36 steel, which is what your bridge and your buildings usually are, sort of 36 KSI yield. Sometimes they use something that's 50 KSI, which is similar to the EH32 that Tom talked about welding in the, what do you call it, the rudder deck or whatever you called it? Oh, the rudder stool. The rudder stool, okay. And there's DH32, and the 32 I think is 32 kilograms per square millimeter, which is actually 50 KSI, okay, as I remember. Okay, it's been a long time since I.
Yeah, it's weird because it all goes up A36, which is 36 KSI, but then DH36 and EH36 are, I think, 48 and 56 or something.
Right, well, yes, because A36 is 36 KSI, 36,000 pounds per square inch. EH32 and DH32 are, as I remember, 36 kilograms per square millimeter, which works out to 48 or 52 KSI, as I remember. But it's been literally 35 years since I've worked on EH and DH steels. They are sort of a marine type of steel. It's basically what the structural welding code would call a 50 KSI steel. I mean, it's the same thing. The steel companies don't necessarily make a different steel for every designation. You have different standards. You have the American Iron and Steel Institute, which is the 4-digit, like the 1021 steel or the 4340 or the 4130 or the 8630. And then you have the ASTM specifications, which are also used by the ASME Boiler and Pressure Vessel Code. They're like A36, ASTM A36, or I showed you out of one of the books, Stout and Doty's book, A27, which is a cast steel. That's an ASTM steel. Well, if they're a boiler and pressure vessel, they make an SA36 or an SA27. But then the Navy has their steels, the HY steels. The Germans have their steels. And what happens is a steel company, a lot of these things have the same overlapping ranges. So if I buy an A106 pipe, ASTM A106 pipe, it might meet a 1020 AISI designation. It might meet a ASME B31.3. Actually, that's actually, well, it might also meet that. Anyway, it might meet 5 or 6 standards. And you can put it on it depends on what you put on your purchase order, which ones are going to hold. In more recent years, people just put all of them on, okay? And sometimes they conflict, okay? Because not every standard is exactly the same. That's another problem. Anyway, but for preheat, if you have a simple low carbon steel, doesn't harden very much, all you really need to do is get the moisture off. And the ASME code says you shall not weld steels with less than 50-degree preheat. Because even though you don't have frost above 32 degrees Fahrenheit, you have considerable amount of absorbed water on the surface. Okay? I mean, where do you think the frost on your windshield comes from? When it gets below 32, there was actually a little layer of dew on there, right? So below 50 degrees, you actually have enough humidity in the air. The surfaces, every surface starts to absorb some moisture. And you shouldn't weld on a surface unless you bring it up to 50 degrees. In 50 to 100 degrees, because let's face it, when you preheat, you're going to overshoot the 50 degrees. And as you start welding, it will start to cool down because you're no longer heating it, most likely. And so it's kind of in that range. You're not doing anything except driving off moisture, okay? And moisture, of course, is a source of hydrogen. But you can tolerate 10 or 20 parts per million hydrogen in these types of steels that have very low preheat. When you go to medium preheat, and I call it 100 to 300 degrees Fahrenheit, now you may have a thicker steel, or you may have a higher carbon steel, or you might have a little bit of alloy content. It might be an HSLA steel that's 2 inches thick. If it was HY80 and it's 2 inches thick or 4 inches thick, you might need 300 or 400 degree preheat. If it's an HSLA, you may only need 100 to 300 or 100 to 200 degrees preheat. That's why the Navy wanted to go to HSLA plate steels, and that's one of the reasons they sent me over to Japan in the mid-80s to see how the Japanese were making these steels. The Japanese were making commercial steels for shipbuilding at the time that required no preheat. So they might have 1 inch thick plate that in the old days with an alloy steel, you had to preheat to 200 degrees. Now they didn't have to preheat it at all, at least during the summer in Japan. Maybe in the winter, they had to get it up here, but they didn't have to preheat it. Saved them millions of dollars in shipbuilding. What happens in this medium range? Ordinarily, if you heat something up, the temperature time plot, when you strike an arc or whatever, well, you get up here to the melting temperature and then it will cool. It'll rise up rapidly because the arc's pretty hot. You take the arc away and it starts to cool down. If it cools down below 100 or 200 degrees, you run into a problem. This is where hydrogen cracking occurs. Remember I showed you hydrogen cracking is worst at room temperature? And if you're at 200 or 300 degrees, the hydrogen can diffuse out. Remember I poured the Sprite in the, okay, get the Sprite is flat. Well, if you preheat, you now are going to level off at a couple of 100 degrees. And so the hydrogen has time, because this big heavy piece of steel is not going to cool off in less than an hour. So you're actually doing a 1 hour post heat by preheating. Okay? Now, one of my favorite stories, I was talking to a friend who was a welding engineer at Idaho National Engineering Lab, out in Idaho Falls, and he was talking about he had gone through a shop where they were building some nuclear reactor components out of carbon steel, and it was a Monday morning, and it was I don't know if it was a pressure vessel or whatever, but he went up and he knew the thing was supposed to be preheated to about 150 degrees because he was a welding engineer. And he went up and he didn't feel warm. I mean, if you stand next to something that weighs a few tons and it's 150 degrees, you sort of can tell, okay? And he put his hand up to it and then he actually touched it. And you can't, if you put your hand on 150 degrees, you won't leave it there very long. You won't burn it immediately, but you won't leave it there. And he realized it wasn't preheated, and he went over and asked the welder who was welding. He says, "Well, did you preheat this?" He says, "Oh, we did that on Friday." Oh, okay. And it cooled down over the weekend, so there was no effect of preheat. Preheat does nothing metallurgically. It just slows the cooling rate so you can get rid of the hydrogen. So basically here, intermediate, you're slowing the cooling to destroy or evolve the hydrogen, get rid of the hydrogen. High preheat, on the other hand, when you're getting above 300 degrees Fahrenheit, which you might have to do on a thick section of an HY 100 or something, in a 4-inch thick, highly restrained joint. We'll see that in a little bit. When you're doing this, you're actually tempering the steel. You're getting a microstructural change. Yeah, it's cooling down just like this, but it's cooling down above 300 degrees. And above 300 degrees, you're going to temper the steel. Remember, I told you, you can take a medium carbon steel, has a high carbon equivalent. We haven't talked about carbon equivalent yet, but anyway. You can take something like this nail file, you can quench it. It'll be fairly brittle and very hard. And then you temper it, you bring it up to 300 to 1,000 degrees typically, or 300 to 1,100 degrees Fahrenheit for a little bit of time, and you soften it. Well, basically what you're doing, if you go to a preheat above 300, you're going to temper and soften. To hopefully less than Rockwell C30, which is a hardness level. So you're going to soften to a lower hardness. And at Rockwell C30, which is about the strength, the minimum strength of something like an HY 130, you usually don't get cracking unless you're very highly restrained. Okay? So higher preheats. Now, we go to, when I say higher preheats greater than 300, you are tempering at 300 or 400 degrees. You're tempering at 500. You're tempering at 600. We tend to avoid, for metallurgical reasons, 600 to 1,000 because you get something called temple embrittlement, which is another problem in the steel, in carbon steels, not so much in alloy steels. But we try to avoid that. HY80 has a lot of, and HY 100 have a lot of alloy addition because they temper them at above 1,000 degrees. They don't want to temper them in the 800 degree range in the steel mill to lower the hardness. You could use less alloying element, save hundreds of dollars a ton, but you're going to not get the same toughness. Okay? It's not that the toughness falls off a cliff, it's just not as good. And we always want the best. So there are different levels of preheat. When you go to some very difficult to weld materials like cast iron, you may have to preheat to 600 degrees Fahrenheit. Well, who wants to weld on something that's 600 degrees Fahrenheit? I mean, if you brush up against that, I mean, you actually could probably start your cotton clothing on fire if you brushed up against it at 600 degrees. You're getting to the ignition point of a number of organic fibers and stuff. You certainly at 600 degrees, any piece of plastic, if you had a polyester shirt, hey, it's not toast, it's melted. Okay, and it's liable to start burning. Okay, you're getting close to the ignition temperature. Some materials that are very, very susceptible to residual stresses and cracking, such as some nickel-based alloys. If I had a turbine blade, I've been to shops where they take turbine blades and they preheat them to 1,000 degrees centigrade, which is almost 2,000 degrees Fahrenheit, in order to be able to weld them, because just the residual stresses from cooling and shrinkage will crack that turbine blade alloy. It doesn't have very good ductility to begin with, and it has excellent high temperature strength. That's why you're using it in the turbine. Okay, so it won't deform in the turbine. And with that high strength at high temperatures, it just cracks. And so they actually weld these things. They actually put an induction heater on it. The thing is glowing red when you do the electron beam weld to repair it. Okay, they do it in a vacuum. It's kind of pricey, but that little blade might be worth $7,000 repaired, and it's worth junk. Actually, it's actually worth about $50 scrap metal. You know, but it's worth $7,000 if you can repair it. So it's worth doing some pretty unusual preheats in some alloys, but not steels. Okay, the highest temperature I've ever seen in steel preheat is about 600, and that's for a very, very thick, highly restrained steel. Most steels are not above about 400, but even that, I told you about the Seawolf and the blue jelly suits and stuff. When they redid the Seawolf, they didn't want to have it crack a second time, okay? So that's why they went to the blue jelly suits. And they actually, I think they shut down production of Electric Boat for about a year. But even that sort of cost a few dollars, because you might be able to lay off the hourly workers, but you can't lay off the salaried workers. They still got to come and eat their lunch in the cafeteria. Okay, actually they had a lot to do trying to figure out how to solve the problem. Okay, any questions on preheat? We're going to go through preheat in spades now, because I just handed around part of the structural welding code. And we're talking about welding something like this. This is, I think I got this from Electric Boat back up about 30 or 35 years ago. This is an actual weld in 1-inch thick, HY80, made by Electric Boat. Has a backing bar because they welded from one side. If you actually measure it very carefully, you'd actually see some distortion here. See if I drew a straight line here, it wouldn't be, the thing is V'd, right? Because it's a V-shaped weld. You can also see the size of the heat affected zone here. This is weld metal in the slightly lighter gray. The darker, blacker region is the heat affected zone of the weld. You got a heat affected zone down here. This piece is probably not HY80. HY80 is expensive steel. If you're just using a backing bar and you're going to cut it off later, use a piece of cheap old carbon steel. Okay? But, and this is not rusted. Anybody want to know why it didn't rust? Because it's black iron, it's actually got a layer of other stuff on it, but the polish surface, we've sprayed it with a clear coat. Okay? Clear lacquer, so it wouldn't rust. Let me also hand around, while we're going to start to talk about how to control preheat. There are lots of books. This is just a single page sheet of carbon equivalents. And I'm going to talk about carbon equivalents. There are lots of books from the 1930s, which 1940s was the first edition of Stout and Doty, I think, on how to weld steels without hydrogen cracking. In the mid 60s, Frank Coe came out with his book from the British Welding Institute, which is sort of based on the research they did because of the Liberty ships at the British Welding Institute. Anyway, there are a number of things, but finally, starting about 10 or 15 years ago, the American Welding Society, which publishes the structural welding code that's been around since about 1920, the two most widely used welding codes in the world are the ASME code, which is, some people call it the granddaddy code. It had its 100th anniversary about 5 or 6 years ago, okay? And it was kind of the first welding code. Arc welding didn't start until the 1880s. Anyway, it actually was invented in 1806 or so by Sir Humphrey Davy, who was using Volta piles, they called them, but they were batteries. And they were a research thing, okay? But Alexandre Volta had developed this electrochemical cell, which he called a pile, P-I-L-E, because it was a pile of plates, okay? And Sir Humphrey Davy had this, and he was studying arcs. In fact, he called it an arc because he had two electrodes, which he placed together, and he pulled them apart, and it formed an arch. That's where the word welding arc comes from. And he found this was a pretty interesting heat source. It would melt the tips of the steel, or not steels, but the materials he had. So, of course, one of the first things, and you'll get this in my fusion welding lecture, One of the first things anyone does with a new heat source is they try to weld with it. Whether it's a laser, the Navy developed particle beam weapons in the mid-'80s to try to shoot down incoming missiles, and they couldn't do anything with it. So in the early '90s, they had a workshop at White Oak to figure out, with peace breaking out with the former Soviet Union, we spent $250 million developing these high-energy electron beams that would go through the air, and they're supposed to shoot down an incoming missile, and we don't need it anymore. What are we going to do with this $250 million technology? And they asked me to come down and talk about whether they could weld submarines. And I went down and said, well, maybe you could melt a submarine, but you can't weld with that much energy, okay, because you only need about 10 to 50 kilowatts to make a weld in that piece of HY80 that's going around. And they had megawatts, okay? The only problem with that high energy electron beam, it worked great in a vacuum, but unfortunately the ocean is not in a vacuum. It's got air above it. And they ran into something called a hose instability, so you could shoot what should have been a straight beam coming out, but then the atmosphere would cause those electrons to whip around like the end of a garden hose that wasn't restrained, that had water cut. That's why the physicists called it a hose instability. And so you actually could shoot down missiles from 30 miles away, but you had to have a very cooperative missile that would run into your beam, okay? You couldn't aim it. They could shoot down something 30 inches away, but they determined that wasn't far enough away to protect the ship. Anyway, it's only $250 million. It was a DARPA project. Don't blame just the Navy, but it was managed by the Navy. Anyway, so the second most widely used, and actually probably the most widely used today, is the structural welding code. In the United States and many parts of the world, you can't build a bridge or a building without using the structural welding code. Not as rigorous as the ASME boiler and pressure vessel code. The consequences of a boiler and pressure vessel code failure is you basically wipe out a whole city block or more, okay? The consequence of a bridge or a building falling down is a few people get killed, a few cars, get destroyed or something, but it's not as serious. So the requirements are not quite as strict. I should have brought you an earlier one. This is the 2010. I think they have should be coming out with a new one. When I started buying these 35 years ago or whatever, they were 1/3 the thickness or 1/4 the thickness, and they cost about $80. Now they cost about $400, because all of the code writing authorities learned in the 1990s they could make a small fortune by charging a lot of money for the codes, because you can't fabricate unless you follow the code, which means your engineers all have to have copies. So someone has to have, how many copies of this code. And yeah, you can have it in digital form, but you still have to pay for that digital copy. So the American Welding Society used to limp along on a couple of $1 million a year, now makes $10 or $15 million a year, not just by selling codes, but by certifying welders, which we're going to talk about in a little bit. It's become big business, and they used to have like $1 or $2 million in savings, and I just looked at the balance sheet in the Welding Journal last week, and they have $90 million in the bank, okay? So it's been a big business for societies, and for a while there they decided this was such a great deal. The boiler and pressure vessel code comes out every 3 years and would cost you $16,000 to buy the whole boiler and pressure vessel code every 3 years. Now they give you semi-annual updates, which comes free with a $16,000 subscription. This only costs $400, but they decided a few years ago to bring out a new edition every year, so they could get $400 from everybody every year. Well, they got so many squawks that it now comes out every 3 years again. Anyway, so the boiler and pressure, or the structural welding code, has included in it for the last 10 or 12 years an Annex I, which is guideline on alternative methods for determining preheat, okay? Preheat is a complex subject, but this is the best by far explanation, and you now have a copy of this. There are two basic methods of determining preheat, which are right down here. There's the hardness control and the hydrogen control. Well, you now know what those mean. Okay, hardness is you don't want it to get too hard, because the harder it is, the bigger that stress circle in that Venn diagram becomes. And the hydrogen control, you don't want to get too big because the bigger that environmental circle gets. Okay? So if I've got this Venn diagram, maybe I ought to draw my Venn diagram, I can either control hardness. So if I have a material and I have a certain amount of hydrogen, which we call the environment, which is really hydrogen, or I could have hardness, and if I can control my hardness, which is my stress, I can get zero overlap, no hydrogen cracking, right? No intersection there. Or I can have my circle of material, I can have a lot of stress, and I can control my hydrogen, and I have no overlap, right? So those are the two methods. You can't, well, you could control the material, but usually some designer, design engineer has told you, you shall make it out of HY100, or you shall make it out of whatever. You could control the material, but that's a whole new design. So if you think about it, well, what else do you have other than those two circles to control? So there's the hardness control in the heat affected zone, because that's where the cracks usually occur, except in the Seawolf, where it occurred in the weld metal, which was a big surprise, because it had always occurred in the heat affected zone before, but they didn't have such overmatching weld metal strength. Okay, so the selection of method, this first one is hydrogen, well, I'm sorry, yeah, well, let me back up. Methods, this is hardness control, and they don't say much about hardness control here. We'll get to it later down here. So here's selection of the method, and the first thing you do is you calculate a carbon equivalent. And a carbon equivalent, I did mention carbon equivalent before. I think I talked about hardness and hardenability. Actually, I didn't do it in terms of carbon equivalent. But if I was talking about hardness, the carbon controls the hardness of a steel, whereas the alloying elements control the depth to which hardening occurs. So if I have a carbon steel, and I told you a carbon steel, it's hard to quench it fast enough to get something much more than a 1/16 of an inch, and that HY80 that I sent around, that had a heat affected zone that's more like a 1/4 of an inch. So I couldn't even get high hardness over that full heat affected zone in a carbon steel, but an alloy steel I can. So if you remember, I talked about hardness versus hardenability. One was a function of the carbon content, the other one is a function of the thickness and a function of the alloy content. Well, the carbon equivalent is basically a measure of how deep I can harden that heat affected zone in that steel with a certain alloy content. So it starts, the hardness or carbon equivalent starts with the carbon, and manganese and silicon don't add as much hardenability as carbon does. You divide by 6. Chrome, moly, and vanadium, you divide by 5. Nickel and copper, you divide by 15. This is one of the formula. Okay? There are many formula. And so out of Easterling's book in an appendix, he lists a lot, and I handed this out. You don't have to be able to read all this from the board, so don't worry about it too much. By the way, we need to, in general, be panning, the screen to get the not on this one, but some of the others, if I'm talking about things on the screen. Here's that same carbon equivalent formula. Here's other carbon equivalent formulas that lots of people have developed over the years. And I know you can't read it from the screen, but I handed it out because it is so busy. And you're going to see that here in the AWS Annex I, they use not just this one, but another one. Okay? So you go through and you look from the carbon equivalent, and it says, figure out whether you are in zones 1, 2, or 3. Well, you read this, let me tell you, I'm going through this in a little detail, because the first time I ever read this, it took me about 3 hours over 2 days to figure out what this thing was telling me. And when I finally understood it, I thought, oh, this is pretty good. But it took me 3 hours to figure out, and I knew something about some of this stuff, okay? Well, you have to now go to this plot, which tells you what zones 1, 2, and 3 are. Okay? So here's zones 1, 2, and 3, and of course it's not the first figure, it's, actually it is the first figure, it's not the first table. Zone classification of steels, carbon content versus carbon equivalent. So I'm plotting carbon content versus, or hardness versus hardenability, if you will. And down here in the low hardness zone, less than 10 points of carbon, I can't get high hardness no matter what. And so I don't, if I want to control hardness, zone 1, those steels are easy to weld. Okay? No matter what their carbon equivalent or the depth of hardenability, because 0.1% carbon won't give me more than about Rockwell C30 or 25, or well, it won't give me more than about what Rockwell C30, let's say. Zone 2, I have higher carbon, well, I have higher carbon, and so I can get higher hardness, but if my carbon equivalent, the depth of hardening is not above about 0.5, I'm in pretty good shape. The good thing about HY80 is it's right about, actually HY80 is right about in here, it's in zone 2. You have to use some preheat. Down here in zone 1, you're going to find you don't need preheat at all in most cases. HY80 is right in here. HY100, higher strength, same carbon, is getting over right up against this line. And zone 3, high depth of hardening, high hardness, potential hardness, and these are the ones that are going to take a lot of preheat. Okay, so the first thing you do in hardness control is to determine whether you're in zones 1, 2, or 3. If you're lucky and you're welding bridge steels and stuff like that, or HSLA steels, you're going to find you're in zone 1, and you don't have to do much more than just come up with 50 to 100 degrees to get the moisture off. Okay? Now, that's the hardness method going through here is you use the carbon equivalent and you look at another plot and determine whether you have a maximum heated zone hardness of 400 or 350 Vickers from figure 1.2. Well, it turns out 400